All right, we're diving into a concept today that is so out there, it might completely change what you think of when you hear the word computer. Forget silicon chips. Imagine a machine that's grown from soil and fungus, a living computer that doesn't calculate an answer, it physically becomes the answer.
So, to understand why on earth you would want to build a forest computer, you have to start with the problem. And we're not talking about just any hard problem. We're talking about a problem so fundamentally difficult that even a perfect, idealized quantum computer would basically just throw up its hands and give up. What kind of challenge are we even looking at here?
Okay, picture this. I hand you a super complex cloud of quantum particles, all interacting with each other in crazy ways. And your job is to just figure out what it is. What's its basic nature? Is it a magnet, a superconductor, something totally new? Well, for some of these systems, figuring that out it's a computational nightmare. The time it would take just scales up exponentially.
And there's a name for this wall we've just hit. It's called QMA hard. You can think of it as the next level of impossible, even beyond what we hope quantum computers will solve one day. And this isn't just some small technical hurdle. It's a fundamental barrier in computational science. It kind of suggests that for certain problems, our entire approach, calculating an answer step by step, is just doomed from the start. So, if you can't calculate your way out of the problem, what do you do? Well, the researchers behind this paper proposed something completely different, a total pivot. They said, what if we stop trying to force a solution out of a machine, and instead we build a machine that can just become the solution? Let's just pause on that quote for a second, because that is the whole ballgame right there. This is the core idea of what they're calling Topo Substrate computing, or TBSC. The goal is not to run an algorithm. The goal is to set up a physical system, let it naturally settle into its most stable, lowest energy state, and then you just read the shape that it's formed. The computer literally embodies the answer. And you can see here, this is a tale of two completely different philosophies. Traditional computers, and yeah, that includes quantum computers, they calculate, they follow a recipe. It's all step by step. This new idea is about physical transformation. You give the system of fungus and sensors a problem, and it physically rewires itself. It relaxes into a final shape, a final topology that is the solution you're looking for. Okay, so how in the world do you actually build something like this? I mean, the ingredient list sounds like it was pulled straight out of a sci-fi novel. You need something to sense the problem, you need something to actually do the processing, and you need a way to get information in and out. So let's break down the three wild components. First up, the triggers. These are these tiny, tiny biological sensors that are actually inspired by how birds can navigate using the Earth's magnetic field. They're unbelievably sensitive. In this computer, they're designed to react to very specific pulses of light, and when they do, boom, they generate a little electrical voltage. This is step one. This is how the problem gets translated from light into a physical signal.
And this is where that signal goes. The processor is a living, breathing network of mycelium. The root-like structure of a fungus. But this network isn't static. Oh no! It acts like something called a memristor, which basically means its own electrical wiring changes based on the signals passing through it. You have to think of it like a self-rewiring electrical grid that physically adapts and grows to process information. It's alive.
And finally, you obviously need a way to talk to this living computer. The researchers are proposing this really advanced light-based system. The simple way to think about it, it's a method for packing a ton of information into a single laser pulse. This super complex light is used to ask the question by triggering those sensors, and then later it's used to read the final state of the whole network. And the paper uses this absolutely brilliant analogy to explain how it all works. Unlike your computer, which has a central processing unit, a CPU, that does all the hard work, this thing is completely decentralized. It's just like an octopus arm that can touch, feel, and react all on its own without waiting for instructions from the brain. Every single part of this mycelial network is sensing and computing all at once. There is no central bottleneck. Okay, so we've got the pieces. These biological sensors, a living fungal processor, and a light-based communication system. So how do you actually assemble this all into a machine that works? Let's look at the actual architecture, literally from the ground up.
It's a layered system, kind of like a cake. Right at the bottom, layer 0, you have the physical stuff, soil that's been seeded with both the sensors and the mycelium. In layer 1, the sensors get hit with those light signals. Then in layer 2, the magic layer, the computation happens as that mycelium network adapts. Layer 3 is the readout, where electrodes measure the final electrical map. And then at the top, you have layers for a classical computer to control everything and a satellite link to send the results back to us.
And right here, this is one of the most staggering figures in the entire proposal. The power budget for an entire field plot of this computer is projected to be 10 watts, or less. That's the same power as a single LED light bulb. Now compare that to the megawatts, millions of watts that a traditional supercomputer or a quantum computer needs. The difference in energy efficiency it's absolutely revolutionary. So, a thinking forest that solves problems even quantum computers can't is an incredible idea, right? But how do you prove it works? You can't just jump straight to recognizing quantum states. You have to start with a more real-world, tangible problem that shares the same underlying physics.
Now, this is a really, really crucial point. The researchers are not saying that predicting wildfires is a QMA hard problem. It isn't. They're using it as a proof of concept. See, this computer is designed to be incredibly sensitive to what are called phase transitions, those tipping points where a whole system's behavior just changes dramatically. And a wildfire suddenly spreading out of control is a perfect, terrifying, real-world example of exactly that kind of critical transition.
So here's how it would actually work. The computer would basically read the landscape. The moisture in the soil, the amount of dry leaves and brush, that's all its input. Then, that living mycelium network physically relaxes into a state where its electrical shape mirrors the most likely paths a fire could take. By watching for sudden, drastic changes in that shape, the system could give us an early warning of critical risk, maybe even 24 to 48 hours before it happens. And I want to be really clear, this is not science fiction hand-waving. The whole project is designed with these incredibly strict, falsifiable pass-fail gates. Every single component has a hard number it has to hit. Can the sensors actually produce a clear signal over all the background noise? If we run the same problem twice, does the network give us a consistent answer? And, the big one, is the final prediction actually accurate? If it doesn't meet these numbers, the whole experiment is a failure. Period. So let's just zoom all the way out. If this works, even if it only works for the wildfire application, the implications are just profound. We are talking about a fundamental shift in how we think about computation and how we interact with our own environment. This is the ultimate vision here. It's not about putting computers in the environment. It's about making the environment into the computer. Imagine a vast, distributed sensing fabric covering the planet, where the act of computing is the exact same thing as the natural process of ecological adaptation. A world that senses and thinks, all at the same time. But, of course, we have to be realistic here. The paper itself is very upfront about the enormous challenges. Those sensor signals are incredibly weak. They could easily just get lost in all the noise of the real world. The network is alive, right? So it's constantly growing and changing on its own, which could be a bug or maybe a feature. And the whole process is probably going to be a lot slower than your laptop. These are huge hurdles they have to get over. But that really brings us to the final thought. Even with all of those challenges, this idea just cracks open the door to a completely new world. If a patch of forest floor can be guided into solving a complex problem, what's next? An ocean current? A colony of bacteria? A weather system? This research doesn't just propose a new kind of computer, it forces us to ask a much, much bigger question. If a forest can compute, what else can?